is a huge upswing, right? You hear all this stuff. Simon talked about it as well. There's so many different applications that X-ray science is approaching that it made sense for us to think about how to make something more local for an X-ray source that could go to universities or labs, and that's what we developed. We got our support through structural biology, and again, this was a slide Simon showed. Protein crystallography was a major driving influence for us to get involved, because the government of the US wanted to help fund technologies that pushed that structural biology, the idea of understanding how drugs work and diseases work, remained a central tenet to their philosophy. We got good support from that. Now, interestingly enough, synchrotrons are really good machines. They ended up doing really well to come up with, stay in pace with demand. So synchrotrons have developed over time. It's become more robotic in terms of automation. FedEx crystallography came on board, which means scientists no longer even had to show up at the beamlines. They could send it, FedEx it with cold samples and get data the next evening. So that's not, it didn't help for local sources like us in terms of getting traction about who we could sell this to. And eventually we sold our first contract to TUM, and Franz is on here, and you're going to hear talks about the Munich CLS. This was our first device that we actually had in a customer's facility to show what a compact light source would work. Now, what happened is that market never showed up in terms of being able to sell these kinds of devices. They're expensive. They're on the scale of $10 million plus when you add everything else into it. So what the company had to do was diversify. We actually worked on EUV for semiconductor people, and they gave us money for doing that. The last straw here was we actually worked with Eli MP to work on a gamma ray source. It's kind of like the big sister to the X-ray source. It's a higher energy ring. Instead of making X-rays, you make gamma rays. Again, it would have been a unique machine. It's very expensive, and unfortunately, it's cash flows problems. Lincian couldn't make it work, and we couldn't get investors to help us work because there was no market for our X-ray machine. So this is what's going to come out in kind of as we ended the company. I'm no longer at Lincian. Lincian doesn't exist. I'm still interested in the technology because I think there is a path, and you guys are hopefully all see that there could be a path for a compact light source. It's now a question of what should the path look like. So I'm going to show you my opinion, which is what I think of the best design is, in quotes here, for a CW source, which means if you're looking just for average flux. Now, this is kind of competing with a synchrotron, which is good and bad. It's good because a lot of applications that have been made as synchrotrons can be adapted to a source like this. It's kind of one-to-one. You can do spectroscopy, you could do imaging. It's just now a matter of figuring out what the right parameters would be to make it work. Now, there are other kinds of ICS sources. People who build these big Joule laser kind of scattering sources, pulsed systems, in order to get snapshots, is a unique angle to synchrotrons. So I'm not going to talk about that. That's not my, I don't know that as well, but I know it suffers in the sense of trying to get as many photons as possible. So pulsed systems are just a challenge, but they do offer a unique advantage. So it has to be weighed in terms of what you think you can learn from that system or what kind of angle you can use it to make a scientific case. So in terms of just a CW source, storage rings and optical cavities, to me, seem the very natural marriage of two technologies. Because it's very high repetition rate. That means you don't need a lot of interaction per pulses hitting each other in order to get a reasonable amount of flux. And the next steps that we were thinking about is designing storage rings, these small storage rings, with essentially high enough energy that they don't suffer from emittance degradation. So low energy electron rings are more difficult to keep in steady state. So you have to keep refreshing them, which is what the Munich source does. Or if you can get above a certain threshold, you can arrange radiation damping so that you can run it more in a steady state, just like a larger energy storage ring. It becomes more efficient that way, The other issue is the optical cavity. And again, people have been working with optical cavities for now more than a decade and showing, I would say, hundreds of kilowatts. My record was about 400 kilowatts of stored power. I know the guys in Munich have already been at 600, 700 kilowatts. So it's about a megawatt scale of stored energy. Now, everything is important because stored energy allows you to have a small cross section. If you have a lot of stored optical power and a lot of stored beam power, you can now arrange it so that you can make this scattering be more efficient. So again, I won't go into details of the technology, but it's there. It's there. It's a niche technology, but it's there. And then my last statement here, which you've all probably heard, is even if you engineer all this really well and you make a nice source, synchrotron storage rings still blow it out of the water in terms of performance. And that's going to be natural because they're big storage. These big storage rings work at it's E squared, B squared in terms of energy and fields. You get a lot of energy converted into photons. And especially in this range of this 10 kilovolt, 1 angstrom scale, synchrotron rings are the path. And keeping on that path is really important. So I like your roadmap that goes 10 years out. We're going to try to get a big source, storage ring source. That is the right answer. And then the question is, what does a small source give you in the meantime, right? So again, I'm going to give you the lesson that we learned at the very end of the day here in terms of where Lincian stopped. We think that a compact light source is really geared towards harder X-rays, higher energy X-rays, the gamma ray system. So the gamma ray is really way up there. That doesn't have a lot of scientific case, but there could be a big sweet spot for X-rays. And the idea is, okay, we know how to build these technologies. We called it, quote, low risk. Low risk means there's a few people who know how to build this. There are places in the world who know how to build this. So the trick is finding those people. That's part of it. You want to find projects. You need the expertise in both accelerator and laser science if you want to make this happen. And then, is it worth it? So I'm going to say, like, is it worth it? Because you need something to help fund it. Either you need governments to help fund it, or you need a business case that says maybe it could be used by someone else. And that's the trick. So I'm going to say, I'm just going to fill this out because what happens is, here we go. I'm just going to fill it all out. If I just look at X-ray energy as a function of what is available in terms of performance. Now, performance means everything. It's intensity, it's spectral brightness, all this stuff. I'm just going to lump it all together. Synchrotrons are way above everybody else in terms of what lab sources can do. And this is what we thought 20 years ago. I still think it, that there's a big gap. There's a huge gap. What kinds of compact sources could fit in that gap? What synchrotrons are really good at, this lower energy range, many beamlines around the world, they do a great job. If you try to compete with that, it's tough. And almost every design that I'll ever come across, it's going to be tough because if it means low energy electrons, it means that the emittance, the quality of the beam is always going to be lower than a higher energy beam, and you'll suffer. So trying to compete at the low energy range is just a hard game to play unless you're doing it for some other reason. If you're just doing it for research or for some particular application, that's fine. But as a general use case, I would say we found that as we go to higher energy, compact light sources tend to be more efficient. They tend to have better quality beams. They tend to produce more quality photons. And at the same time, synchrotrons have a harder time creating high energy beamlines because now you start have to use harmonics of undulators, and you have to worry about a lot of power and then filtering it. So it now becomes a better game to try to say, well, if we can approach high energy X-rays as a target for a compact light source, we can now actually compete with synchrotrons and maybe synchrotron science. There's fewer beamlines, that's for sure, but there already may be some applications that could work there that have not been tried as much because of the scarcity of synchrotrons. And again, you'd have to go to the X-ray guys, the X-ray applications people who might think, oh, well, what if I did have a 100 keV beam? What would it give me instead of a 10 keV beam? I'm going to throw this table out. I'll throw these slides to somebody here, Lawrence or Simon. I'll send this out to you so you have an idea. But we thought about this, and the idea was, what would a next generation CLS look like for us? If we were a company that could promote it, this is what we were going to propose. We were going to say, let's not do what we did before. Let's try to build something that has higher energy, go up to higher energy electrons, and then work instead on laser technology. 1 micron laser technology, solid state technology, is a workhorse in the laser world. There are so many different systems that have like mode lock lasers around 1 micron, YAG and everything else. However, there are new kinds of concepts coming up that might be 2 micron. There's thulium, holmium, there's other kinds of semiconductor lasers that could work. What does that buy you? That factor of 2 buys you a factor of 2 in X-ray energy. So for the same electron beam energy, you can get a factor of 2 difference in X-ray energy. Slightly longer wavelengths help, because if you're going to target a certain energy, let's say 20 keV, you'll want to work with a slightly higher energy electron beam. And that's why a longer wavelength laser could help. So we started looking at what it would take to get performance at these different levels. So again, I won't go into the details of this technology. You got guys in the audience here who know how to do calculations about this stuff. It should be pretty straightforward. We already had CAD drawings. Again, this is just as a cartoon to show you how far we went. But the idea is that the accelerator systems, just like you showed at your other systems, accelerators have been around for 40, 50 years now. They've been optimized. So I know guys at Slack, the guys like Valery Dolgashov and Sammy Tintawi, they now know how to make efficient room temperature S-band, C-band accelerators. The costs now are mostly just power supplies, big modulators. You got to fire these things and run them. That's the expensive part. Storage rings also have been around now for decades. So the ability to model and design magnets, combined function magnets. So you're talking about like your MBA lattice for your big storage ring, have combined function magnets. You can build smaller combined function magnets to do small storage rings and get very high performance. The trick is to get enough energy. So you want to be able to run these storage rings at enough energy so that you can treat them just like a big storage ring. You can have a top-up mode. You can run them continuously. You can do all sorts of tricks with them. You can run with RF, lower frequency RF cavities to have long bunches. There's a whole bunches of things, tricks you can play that make it tailored for compact light sources. And here's just another cartoon of same thing. This is actually from a real simulation, but now just translated into a cartoon. There's other geometries. We made one that would be compatible exactly with our current optical cavity we have, let's say in Munich. So it just needs to be tailored so that the harmonics all match. There's rooms for putting in damping wigglers. There's all sorts of, again, there's well-known techniques, but this requires accelerator science. It requires people who know how to build storage rings and specifically know how to do magnets to be able to do this kind of machine. But it's doable. That's what we for, especially for high energy, this is something doable. So this was, I found this slide that Michael Fesser gave to the UK community workshop. So this is probably you, Simon, and others. This was back in 2020. So we've already been thinking about this. We want to make, what does something that can go to higher energy open up? And we talked about some of these things. So there could be high flux densities. There could be for imaging. There could be different, there's a window of opportunity that could be new. And that's usually a good sign. That means that you could try to find people who are interested in building this in the synchrotron community already. If you try to just build something that synchrotrons can do now, it'll be harder to get support from some of these people. If you can build something that adds to it, complementary, then I think there's a higher chance of getting, I would say, the experts involved and getting applications developed. So I think this is an opportunity for anybody if they can figure out how to make this, get funding and find a place to put it and get people on board. So my last slide here, essentially cautionary tale, is we've been at that. We were at it for almost 20 years. It all sounded good. It's attractive. The scientists, when we go pitch this and give a talk, all like it, right? The technologies are neat. It's fun to work with, but at the end of the day, it's still there's know-how and knowing how to make the source. So what Simon showed and others show about synchrotrons are that big suite of applications everywhere. That is just the X-ray science, but how do you actually build the technology? So this is the problem. I think it's a problem for you guys as well. How do we get the technology, I guess, closer to the customer? Because it's somewhat niche technology. And the problem is there aren't now businesses around there. We were one of the few businesses that sold this as a product. It's hard to find businesses like this because there's not much market. It's expensive, as I said here. There is no industrial need that we found, which means it's going to be a scientific tool. That's okay. But it also requires, from the customer side, from the user side, a commitment to infrastructure, to personnel, everything. And probably Franz and the Munich guys will talk to you about this. It's a system. It's not just the tool. It's a whole facility. And you have to now, it's basically owning your small little synchrotron. You've now got to manage that system. You can't just go there. So that's the competition. That's kind of what I noted here is the competition is most people can go to a lab. They can go to a synchrotron and rent their X-rays. Why own it? That's an extra burden. It's an extra potential that has to be met. And trying to do that with help is what I consider one of the core tasks for you guys to think about when you think about it. A competent source is not just getting it built and sticking it somewhere, but how do you actually make that into a system that is alive? So I think, again, it would be great to have it in your backyard because it has all these opportunities. You get to learn about the how it runs, how it's built. There's people who will learn about accelerator science there and laser technology. But this is the key point: the ability to partnering with somebody to share that development costs. That's why I'm thinking about what's the angle. What can you guys do to make something new, to get other people involved that says, yeah, this could actually help the community, not just locally, but everywhere. So that's my pitch. That's it. Thank you, Simon.
Hi, I'm going to take over the moderating duties since Simon's in an inconvenient spot for that. But I guess we had to swap out the talk that was after Rod. That's why it says discussion right now on the program. So we can either ask Rod a few questions, or we can just go to, I think, Fabio, who's the next speaker. Or I see that I saw Phil was here. I don't know, Phil, if you had any reactions to Rod's presentation.
No, I thank you. Thank you for, it's nice to be here. No, I think you made some very good points. I think one of the things that came out in the UK was this idea of a grid of compact light sources, each one maybe doing slightly different things. So you have both the regional benefit of having being a partner, as to use Rod's expression, in light source development, but also allowing you to then have different types of facilities across the, in this case, Great Britain, but in your case, South Africa. So I think that's something you might want to think about. One of the advantages, you can take some of the benefits of having a synchrotron, but put them strategically around a number of places, and that would help in terms of training and development and enable you each one to have a slightly different focus. But I think I agree with what he says, and I think also it's important to look internationally, because now there's no one place you can go and buy one of these machines. So I think thinking about maybe how one could be part of a global push in this area is something you might also want to think about. But those are the main things, and I'm obviously very, very excited by the fact you've got a group together and to know that we're not speaking on our own. So it's great to be here.
Right now, so any other questions? I just have one comment. If there's no questions, there is so there's a SmartLick project in the Netherlands, and then there's the CXL project at Arizona State. where do those fit in the sort of towards the next generation CLS? Or maybe their current generation CLS. Anyone have a?
Sorry, I just want to say, you know, we got a panel discussion at the end, and I think we could have a very, very good discussion about this, and maybe just collect the inputs from our other panelists first.
Okay. So I don't know if Fabio's ready to, if we can jump ahead of the schedule a little bit and go with Fabio, who I can make presentation. I thought I saw Fabio here somewhere.
I think he can share his. Or
I don't even see him.
Okay.
I thought he was here earlier.
I think if Fabio popped off, maybe we could go to Luca and come back to Fabio.
Okay. Is Luca here?
Yeah.
Yep.
It's here. Good afternoon. So
Okay.
Should I start? Let me check. Share screen. Share. Okay. Do you see my screen?
Yes, we do.
Is it in
Presentation mode.
full screen? Oh, great. Okay. So yeah. Good afternoon. I'll try to recap as quickly as possible the experience that we developed in building the STAR research infrastructure based on inverse quantum scattering source using a LINAC plus amplified laser scheme. And I try to use this experience to clarify some open issues on the way of developing an African regional infrastructure based on a compact light source. Clearly, not everything I will say will have a general validity. About quantum light sources, I will try to underline pros and cons, issues and challenges and benefits. So first of all, I'll go through a brief recap of the linear physics of ICS because it's important in order to understand very basic limitations of compact light sources based on quantum scattering as those mentioned by previous speakers in terms of achievable fluxes, bandwidth, and so on and so forth. I will have a very quick comparison between the three possible paradigms that we can adopt for building a compact light source based on quantum scattering. Then I will go through an illustration of the STAR project in terms of present status and the challenges we had to address. And I'll try to better underline that this experience may be a good inspiration to develop the African regional user facility based on compact light source, and this can be a good first brick toward the general African light source. Okay, very quickly, all radiations that is emitted by relativistic electrons is affected by this very challenging issue, the energy angular correlation. So photons emitted at some angle have a different energy than photon emitted along the nominal electron trajectory. Also, collisional radiation is affected by this point. In fact, we will focus today on these inverse quantum scattering source coming from the collision between a relativistic electron and an optical laser. But I can tell you about many other kind of radiation or secondary beam sources based on electron photon collision that are all affected by the so-called gamma square theta square issue. In case of a LINAC-based quantum scattering source, the typical scheme is a photoinjector driving a LINAC up to, to a moderate energy in the range of 100 MeV, colliding with an optical pulse carried by a laser, generating X-rays in a fashion that is very similar to an undulator type radiation that is typically operated with GV class LINACs or storage rings. So very quickly, the energy of the scattered photons in a quantum scattering source are sort of specified by the fact that the wavelength of the incident photon carried by the laser in the electron-less frame is boosted or blue shifted by a factor 2 gamma due to the Lorentz transformation. If the scattering is inelastic, so if the electrons does not recoil in scattering back the photon, then in the Thomson limit, we have to multiply by another factor 2 gamma that gives us the very famous 4 gamma square Lorentz boost factor connecting the energy of the incoming photon to the energy of the backscattered photon. And this is very good characteristics of the quantum backscattering. The bad feature is that what happens to a photon that is scattered not exactly at theta equals 0 along the direction of propagation of the colliding electron? Well, excuse me, these photons will be redshifted. So the wavelength will be longer by a factor scaling like gamma square theta square, such that when the angle is of the order of 1 over gamma, the energy of the scattered photon is 1/2. This is clearly a bad characteristic of the scattering because it makes such that a radiation source based on this quantum backscattering is intrinsically polychromatic. So we have photons at all energy going from the quantum edge, that is a famous 4 gamma square times the energy of the incoming photon, divided by this redshift effect. There is also another effect due to recoil, but this is not important in all compact light sources that we are considering. Even for gamma rays generation, like in LINP, this factor is very small, so it's sort of negligible. There is a new generation of X and gamma ray sources that is on the horizon, working at recoil factor very large, but this is a new story, and it will be the next probably generation. For those of you who are really curious, you can read this paper that we just published on fundamental plasma physics about symmetric quantum scattering. But I don't have time today to discuss this strategic new vision. So, because we are dealing with the polychromatic radiation beam, we have to monochromatize. Clearly, because of the energy, the typical monochromatization applied in quantum backscattering sources is a collimation. I will show you the effect of a virtual collimation here. For example, at STAR, if you run a 140 MeV electron beam and you collimate at 1/2 of a milliradian, forgive me, I apologize about this bad font. This is 510 to -4, so 1/2 a milliradian. You will have a bandwidth of about 1.4%, and this number of photons per pulse, and this will be the spectral distribution, a nice monochromatic beam line. If you increase the collimation angle from 0.5 milliradian to 2 milliradian, you get a spectral line that is less monochromatic, still probably adequate and good for many imaging applications, but this is an important characteristics of the compound backscattering source that brings to this angular correlation of the photon energy that is intrinsically an intrinsic characteristic. This brings to the emittance. The emittance of the electron beam plays an absolutely crucial role. Here you see what happens at the spectral line if you collide an electron beam with small emittance. You have a nice narrow bandwidth spectral line, and if you increase the emittance, you have an inhomogeneous broadening of the spectral distribution that is at all similar to what happens in a free electron laser. A free electron laser needs a very low, very small emittance beam, exactly because this broadening due to emittance that is sort of the inhomogeneous intrinsic angular spread of the electron crossing the interaction focal plane. This effect in free electron laser can kill the instability. In inverse Compton scattering sources is not killing instability. We are running a linear, incoherent, spontaneous emission source. The problem is that, as you see, the bandwidth, the relative bandwidth of the Compton scattering radiation is strongly dependent on the normalized emittance of the electron beam. And this brings to a very well-known criterion for optimization of the luminosity that goes under the name of Petrillo-Serafini criterion, which you see that spectral density, that is the real quality factor of a photon being used for imaging, spectral density that is typically given in number of photons per second per electron volt of bandwidth. You see spectral density scale like brute force in the numerator divided by beam quality in the denominator. So this is the normalized emittance of the electron beam. This is the average current of the electron beam, that is power, that you bring to collision, and this is the energy in the carried by the laser pulsed interaction. It's also interesting to see that basically spectral density scale like the brightness of the electron beam times the energy of the laser. For other applications like microscopy or spectroscopy, the average brilliance is probably more important, and it's interesting to see that the scaling of the brilliance is like the ratio between the spectral density and the emittance of the photon beam, which is clearly given by the spot size times the collimation angle. So if you can focus strongly the beam, you get a larger brilliance that is well known. Okay, so what are the three paradigms? There are many others. I don't want to be complete here and exhausted in my overview. We have the easy way to do Compton scattering, that is STAR, AfLS at the Arizona State University, Smart Light in the Netherlands, ATF at Brookhaven. There is another ongoing project at UCLA for gamma rays. There are many of these. This is easy because you just need to run a LINAC. Well, a LINAC with a photoinjector capable to generate low emittance electron beam. You have seen how crucial is the emittance of the electron beam. So the smaller the emittance, the similar performance you can get here in the interaction with the laser with lower beam current. That means lower beam power, more sustainability, and more, I would say, simplicity of operation, also from the point of view of radio protection issues. The difficult way, well, I'm not spending so much time because previous speaker was very nice in describing how it works basically. So it is a full energy LINAC injecting into a storage ring. Oh, this is, by the way, the TOMEX French project that is coming alive these days. The very difficult one is the superconducting ERL solution that we are not discussing. So I want to summarize, just as a personal point of view, what are the pros and cons of storage ring-based ICS compared to LINAC-based ICS. Well, the first one I see, and it was also pointed out by previous speaker, is that for these fancy megawatt class optical Fabry-Perot cavity, you really need a laser guru. A laser engineer probably is not enough. I know personally because for this ERL project, one of my colleagues here in Milano working on quantum entanglement was developing one of these Fabry-Perot cavities, so I personally witnessed the complication and the challenge of this guy. For LINAC-based inverse Compton sources, you just need commercially available picosecond joule class ytterbium arc laser system. There are several industrial vendors. I don't want to mention the names in order to be politically correct, but at STAR I can say that we had a French company delivering the laser system. A big point that I realized very recently, in storage ring, you can operate only one photon beam light. And to me, this is a limitation. While in LINAC-based inverse Compton scattering sources, you can operate several beam lines. At STAR, we have 2 beam lines that in single bunch mode will be operated alternatively, 50 Hertz each of the 100 Hertz repetition rate. But you can certainly operate, going to multi-bunch mode, the LINAC-based ICS with several beam lines simultaneously. This is simply due to the physics of ICS. The laser pulse is transparent to the electron beam. So you can focus and refocus quite a bunch of times. And this was also demonstrated experimentally in the context of DLI and PGBS, the gamma beam system designed and proposed by the Eurogamma's European collaboration. LINAC-based ICS, because of the emittance, the normalized emittance of the photoinjector, are definitely smaller than those of storage rings with this moderate energy. They can operate with smaller spot sizes, typically in the range 10 to 20 micron, while storage rings are in this larger range. And this is important for phase contrast imaging application, as we know, because the transverse local coherence scales like the inverse of this number. Okay, last but not least, the LINAC-based ICS costs less for the same photon energy, clearly, and is also scalable easily to higher energy. And something that I realized very recently is that with LINAC-based, you can run 2-color X-rays on a very short time scale, bunch to bunch, pulse to pulse. Okay, so let me say a few words about STAR. So STAR is stays for Southern Europe Thomson Source for Applied Research, has been built and developed at the University of Calabria, that is one of the most important universities in South Italy, with the main aim of cultural heritage non-destructive analysis using these hard X-ray beams that will be generated. if you look at the video, we'll give you a view of what inside the bunker. And inside the bunker, we have a 150 MeV LINAC driven by a photoinjector with 2 beam lines, 2 independent interaction regions where the ytterbium YAG 1 joule, actually 500 millijoule interaction laser is taken to collision with the. And so there are 2 beam lines. You see one for high energy and the second is for low energy. Let me go through quickly. Clearly, you need, in any case, a laser clean room and some dedicated effort for the amplified laser system. That in any case, it is you can find by industrial providers. Another very important properties of a star is that the time structure is on the picosecond scale, 2 to 4 picosecond, but in some special operation mode, we can go using velocity bunching technique in the electron LINAC in the photoinjector. We can go to sub-picosecond pulses. It is clearly tunable in a wide range, 20 to 350 kV. The bandwidth can be easily controlled. And it will have linear and or circular polarization with a very large degree of polarization. As I said, because of the very small circular spot size, the local coherence will be quite good. I have 2 or 3 more slides, so I will conclude quickly. This is the layout of the 2 experimental arches for soft X and microtomo. So this will be the low energy beamline coming from inside the bunker and going through the 2.5 meter thick concrete wall. The 2 beam lines and experimental arches have been developed and built by partners of Unical, like Electra Synchrotrometry Est and ASF Metrology. This is a view of the big, thick, heavy granite based micro tomograph that will support samples and detectors for the high energy applications. Let me go through these. Of course, all of these will be embedded in the general control system of the whole machine. And I'm concluding with the cost book. So what was the cost of the source? This is the cost of the ICS source. You can see here the numbers, and here you can see roughly the dimensions of the bunker and the hosting building. This is the laser clean room, the RF powers, racks, and the bunker hosting the LINAC. This is an exercise that I have done recently. What would cost a 170 kV X-ray ICS sort of copied or replicated from STAR? These are a very, let's say, first order approximate cost. There is an important consideration to do. If you have to build a 4th generation synchrotron light source, you will need in any case something like a 150 to 100 MeV LINAC injecting into the booster that ramps up the electron beam to inject into the main storage ring. So if you need in any case a 100 MeV or 150 MeV LINAC, what you can do in the evolutionary way toward the AfLS, 4th generation light source, is to equip the LINAC with a collision laser, with a radio frequency photogun that is not strictly needed for injecting into the booster, and with some other ancillary equipment and X-ray beamlines, so that a good fraction of this investment will be ready to go for the construction of the big machine. Not only this first step could be a very important and strategic initiative to build up the expertise. And I share definitely with previous speakers the consideration that in order to develop this machine, you need an operational team. You need a lot of typical expertise that you find in an accelerator division of a big laboratory. My laboratory, Frascati NFL National Laboratory, or if you go to Brookhaven, to any, let's say, big national laboratories working on accelerator. So this is sort of the minimum list of expertise that you would need to start the construction of a CLS. But these are also, by the way, the same expertise that you need to develop and to run a fourth-generation light source, clearly at a much larger scale. So probably you would have to multiply this number by some relevant figures. But in any case, this is the spectrum of the team that you need and the expertise that you need. And with that, I thank you for your attention, and I address you to this nice overview paper written by my colleague Vittore Petrillo recently. For those of you who are interested in many more details that I didn't have the time to discuss today. Thank you.
Well, thank you. Are there any immediate questions? If not, we can go to Fabio, who is back with us.
Okay, let me stop sharing.
Yep.
Yeah, stop sharing.
Yeah. Good afternoon, good morning, everyone. Can you confirm you can hear me?
Yes.
Perfect. I'm just trying to put my presentation in presenter mode. Yeah, okay. Great. Well, thanks for the invite. To come here today and discuss about a bit simpler lab scale than what I just seen from the previous talk. So lab scale X-ray facilities. My name is Fabio Masiello, and I'm responsible for X-ray diffraction. So I'm a group program manager for X-ray diffraction at Malvern Panalytical, based in the Netherlands. Just a quick overview of what I want to present today. Very briefly, the interaction of X-rays with matter, and then we will go into a bit more details of different scattering techniques. That will be a big part of my talk, also given my current title and the XRD background. But I will also look a bit into spectroscopy, imaging, and then some more exotic combination of techniques, and then briefly some conclusions. So a very simplified view, not exhaustive, of the interaction of X-ray with matter. And we forget the high energy where you have a lot of the other interesting phenomena. But we can see three type of interaction: elastic scattering, where the energy of the scattered photon is the same as the incoming photon, and that's the Rayleigh scatter. You have inelastic scatter. You can divide two types of inelastic scatter: the Compton scattering and the photoelectric effect, and this will be at the basis of, for example, X-ray fluorescence type of measurement. And then you see that all these X-rays that have been absorbed by an object because of some of the interaction I mentioned before will provide the basis to perform imaging type of techniques like radiography or computed tomography. So start with the X-ray techniques, X-ray scattering techniques. I mentioned before X-ray diffraction, where we can separate it between single crystal X-ray diffraction and powder X-ray diffraction. And then I would say the method based on powder X-ray diffraction. They're just giving you some different information. I will cover quickly residual stress, texture, and high resolution XRD. All of these techniques need a crystalline sample or a polycrystalline sample. in case of powder diffraction, they will not work with, for example, amorphous samples or liquid or anything. Other X-ray techniques, X-ray scattering techniques that I would like to cover today is small X-ray scattering, SACS, reflectivity, and we'll also touch on total scattering. And for those type of techniques, you can use actually any type of sample, not only crystalline samples. So starting with the single crystal XRD, that's a technique that is solved to solve the structure of unknown compounds. Require large between commas. I mean, what is large? For lab scales is in the order of 100 to 500 micron. It can be smaller for synchrotron, for larger scale facilities, but still rather large ones, crystal typically. And you see on the right side here of the presentation, particularly of your crystal, you impinge it with X-rays, you get diffraction pattern, and then in your structure solution, you will try to fit some phase and refine it, and until you get the atomic model that best explain your diffraction pattern. It's a very broadly used technique in various fields of research. It includes chemistry, physics, material science, but very much also used in biology in solving protein structure, which is one of the main topic for this technique. Moving to powder X-ray diffraction, which I mentioned before, you need a polycrystalline sample. And this technique is mainly used to find out, well, first of all, what crystalline phases are present in my sample. So this is what we call phase identification, phase ID. You can also see on how much of each phase is present in my sample, so phase quantification. It can be also used as single crystal diffraction to solve structure of unknown compounds, and it is also used to determine crystallite size and strain in your crystals. In this case, the sample is made now of many small. Again, definition of small in this case is ideally you want crystallites that are between 1 and 10 micron. And again, it is a very broad application field. It's really used in field of research such as mineralogy, geology, environmental science, material science, engineering, and biology. Is also very much used as a quality control tool, for example, in several industry, pharmaceutical. They would look at how an API, for example, developed in time under different humidity or temperature conditions. Building material, it is used as a quality tool to see what's the quality of the cement that has been created. And on the right side, just some ideas on how such an equipment could look like. Moving a bit on different type of topics, residual stress. So the definition of residual stress are the internal stresses that are present in a material. So here we're talking about solid object made of typically polycrystalline solid object. And the residual stress are the stress that are left after the external loading have been removed. So when you manufacture, so different manufacture process can contribute to change in residual stress, and also there are a way to engineer your component or your coating, for example, in a way to have stress that, for example, closes itself when there is a scratch or something like this. So it is actually people look for a certain type of stress. Determining the distribution of stress is important, because if there is a high residual stress, that can also, in certain parts, can also lead to premature catastrophic failure. ADXRD is one of the tools that are used to accurately and non-destructively measure residual stress. And on the right side, you see, for example, a screenshot of a software that can measure stress. So particularly, you look at the position of a certain peak, typically high-angle peak, because they're very sensitive to this spacing, and with, for example, inclining with inclination of your sample. Again, staying in solid object, polycrystalline solid object, we can perform measurement called texture. And the texture of a material it refers to the relative orientation of the grains inside the material. So again, I'm talking about polycrystalline solid object. And again, the texture of a material can influence strongly the mechanical and physical properties. Again, XRD is a perfect technique to measure this texture by measuring the diffracted intensity under various geometrical conditions. So, for example, on the right side, you see what we call pole figure. Practically, it's an idea of intensity of a certain peak, for example, 110, 200, as a function of let's say sample orientation. And then by making use of this pole figure, it's possible to reconstruct things like ODF and get an idea of how the crystallographic texture in the sample is. Again, it's something that people are looking even in additive manufacturing. They're very curious. There are ideas on how to modify the texture while printing a 3D part in such a way that you can modify locally the mechanical performance of your 3D part. Now moving a bit again into the realm of more single crystal, there is a whole bunch of technique which make use of what's called high resolution X-ray diffraction. Here, high resolution means that the beam is monochromatized, is highly monochromatized. So while in powder diffraction, you typically use a beam that has several wavelengths, for example, K alpha 1, K alpha 2, and let's say a bit of a Bremsstrahlung. In this case, you really want to have as monochromatic as possible because you're looking now at typically single crystal, and you're looking at epitaxially grown structure, so multi-layers, as it indicated here. These films are very close to nearly perfect crystalline film, and they have typically a low dislocation density. That's why you need such a higher resolution. And what you do practically, again, you're non-destructively manage to analyze this layer in nearly perfect crystalline structure material. The parameters that you are looking for in this case are layer thickness, composition, whether the layer has strain or is relaxed, and the quality, the structural quality. Some of the techniques that are fall under the realm of high resolution X-ray diffraction are rocking curves and reciprocal space map, as you can see here. For example, some reciprocal space map and some rocking curve of some multi-level structure. And this is very much used, as I mentioned on the top. Semiconductor devices are, for example, your LED that you use every day. It is formed in this way. Now we move away from the crystalline realm, and we can start looking to small angle X-ray scattering. This is a technique that measures the intensity of X-ray scattered at small angles. Typically, the range that is used is from 0.1 to 5 degrees. So there is a SAX signal. So like we see, for example, in this is a SAX signal coming from one of our equipment. Is observed whenever there is a structural features in the length of the scale of nanometers. So now we go even smaller length scale in the range of 1 to 100 nanometer. As I mentioned before, the samples that can be studied by SAX is much more broad. It includes liquid nanoparticle dispersion, colloids, nanopowders, biomacromolecules, and more. And from SAX, what you obtain is the nanoparticle size distribution. For example, here you see this is a mono distributed with a certain particle radius, but also particle shape and particle structure. In this case, you see, for example, that with SAX, it's possible to differentiate whether this particular protein is in a tetramer or monomer configuration. Another technique that is very much linked with X-ray scattering is reflectometry. We go again back into thin layer structure, but in this case, they don't need to be again crystalline. It works with any type of, as long as there is a different density between the layers. And it is used to characterize single and multi-layer structure, for example, in coatings, magnetics, semiconducting optical materials, among others. And the parameters you're looking for by using X-ray reflectivity is thickness of the layer, the density of the layer, and also what is the interface and surface roughness. And these again a typical profile for in this case a one layer deposit on a substrate plus actually 2 layers, sorry, on a deposit on a substrate. Total scattering, is also known as pair distribution function, provide information from disordered material. So we're really away from the crystalline. Actually, it can also be used with, it's called total scattering because you can actually use to see both the crystalline part as well as the non-crystalline or disorder part. So like I mentioned before, from the Bragg peaks in a diffractogram, you will get the long range order of the atoms, and the short range order. So the local atomic structure is present in more the broad, less defined features in the diffractogram. And by using total scattering technique, you can actually get what is the local structure, and it's trying to be represented here, where practically you get this type of intensity peaks in your total scattering curve, where there are atoms that can, let's say, at a certain position where there are atoms in your local order. So this concludes, let's say, the first part of the talk, which was on X-ray scattering techniques, and we're going to go now to X-ray spectroscopy techniques. So I mentioned before, in this case, inelastic scattering is used, and we will look briefly at X-ray fluorescence as one of these techniques, and then also something that has been, I think in the last few years, also becoming a lab technique, which is X-ray absorption spectroscopy. So X-ray fluorescence spectroscopy is a method that allows you to determine the chemical composition of a sample, so which element is inside of my sample. The materials that can be analyzed are quite broad: solids, liquids, powder, filters, and fusion bead. It's quite a precise technique with 0.1 to 0.3% relative accuracy, precision, and also very accurate. You can go from low limit of detection of 0.1 ppm up to the full 100%. So that's quite a feature of the technique. As I mentioned, there are two different, let's say, configuration for X-ray fluorescence instrument. One is a so-called wavelength dispersive X-ray fluorescence technology, where practically you have a X-ray tube, which produce mostly using the Bremsstrahlung curve, will irradiate your sample. And like I mentioned before, there is a possibility that some electron are kicked out and some other electron will occupy the free space, the vacancy, and therefore create the so-called characteristic X-ray line. And then by using an analyzing crystal and a detector, which is just a counting detector, you can look at different energy by turning the analyzing crystal, and you can practically look at what characteristic lines are inside my sample. The other technology used is so-called energy dispersive X-ray technology. So you see that the setup is simpler. There are no moving parts. And in this case, what is used is the very high energy resolution of the detector. So again, the sample is irradiated with a white the polychromatic X-ray beam, but all let's say the incoming beam is recorded by this detector, which is now an intelligent detector, SSD type, for example, detector with high energy resolution, and it allows you to see already in one shot all the different characteristic line in your sample. If we compare between the two, so you can see it also from the plot. In the wavelength dispersive XRF, you get quite very good resolution. Especially resolution is determined by the full width of maximum of your analyzing crystal, while in energy dispersive setup, your peaks are a bit more broad. Compared to the wavelength dispersive. The element range is also a bit larger for WDXRF, going from beryllium all the way to uranium. The detection limit are better for WDXRF for let's say light element, but it's for EDXRF are better for the heavy element. And also the sensitivity is better for the heavy elements in the EDXRF and better for the heavy element in WDXRF. The cost, WDXRF is quite more expensive than a EDXRF, also because less moving part and cheaper. And also in terms of operating cost, the power consumption of WDXRF is much bigger than the EDXRF. And then just to conclude this part on XRF, where XRF is used, well, it's quite a broadly used in many industrial processes, in QC and process control, lubricating oils, mining minerals, in building materials. I mentioned before cement as a application space where XRD is important. Well, XRF is also important, and typically, when possible, the combination of the two is actually ideal. But also metals, pharmaceutical, and cosmetics. Everywhere where you want to be sure of the elemental composition of your sample, there will be an XRF machine used. Mentioned before, an extension on the let's say inelastic scattering method is the X-ray absorption spectroscopy. In this case, you obtain element-specific information because practically you are going to use again a tube with multi-target or wide beam, a crystal, and then you can actually change the energy during your scan. And ideally, you will position yourself where there is an absorption edge, therefore get a lot of information which is typically related to one of the element in your material. As you can see here, it's element specific. It's possible to tune in the energy. So for example, from titanium, vanadium, chromium, etc., you can see that the edge are different. So you can actually look at the environment around a specific element in your sample and not so much the other environment. It is also a technique that is sensitive to the oxidation state, as it is shown here. For example, you can recognize the difference between iron 203 and simple iron foil. Also, in this case, doesn't need long range order limit like total scattering for scattering. It can be used on any sample type, and it is sensitive to the local structure of the element being probed. We move now to the last part of my talk, which is the absorption techniques. Well, the very easy radiography. This is, as most of you know, the hand of the wife of Röntgen. So I'm not going to spend too much time on this. And tomography, which is practically an extension on the radiography technique, where practically you have a sample, you rotate it, you collect images at all possible orientation, and then you can reconstruct it by using computer programs. You can reconstruct the 3D and actually see inside your part. If I focus only on computer tomography, you can look at two different ways to look at the data. You can actually look at the voxel base, so you really look inside your part, and this is for visualization, for example, function testing, but also non-destruction testing when you look at defect analysis, or you can also look at surface base where you look at simulation. Some people might be interested in reverse engineer, so you get the look of the part, or if you want to look at something and then 3D print it, you could use something like CT, but also use as metrology, comparing what the nominal and actual measurement of a part are. And then, yeah, for the exotic techniques, I think also something that is coming now more and more, also in the lab scale, is the combination of information. For example, if I look at XRD CT, it's a combination between CT and XRD. So you actually not only are getting an information on the 3D structure of your sample, but you also can grain by grain get information on the single grain by using X-ray diffraction combined. So that's something also that is now available in lab scale type of instrumentation. And I mentioned it briefly before, but the possibility to perform many of the techniques that we mentioned before, both for X-ray scattering as well as fluorescence in operando or during in situ, for example, different temperature and different conditions. And this brings me to the conclusion of my short presentation. It was a short introduction to many. I don't think I've been exhaustive, so not all the techniques that can be performed using more conventional X-ray instrumentation in a laboratory. Many of these techniques in the past were possible only in large-scale facilities, like I mentioned before, XIS. But thanks to progress in source, optics, detectors are getting more and more available also in the lab facilities. Something that I haven't touched upon, but I would like to highlight now is that in case that the requirements in terms of speed or resolution cannot be met with a lab scale facility, And there is really a need for a large scale facility. Having data that are already collected on samples using conventional lab instrumentation is really a good way to help making a strong beam time request. And also, finally, the lab scale facility are an excellent tool to train the future user and scientists of large scale facilities. As, for example, the example of X-Tech Lab in Benin is one good example of that. And with that, I'd like to thank you all for attention.
All right, thanks a lot. Is there any immediate questions for this speaker? That's not a question, but a comment. So why don't we can go on to the next speaker, which is France.
Sure. Here I am.
I make you a co-host so you can share. Yep, go ahead.
I'm trying. Can you see the slides now?
Yes.
Okay, wonderful. Thank you everybody for having me here today and for being able to share our view, our perspective from Munich, and our particular perspective on compact light sources, compact synchrotron sources, their principles and applications, of course. I'm representing a larger team and a couple of people are online, in particular Martin Dierolf, Klaus Achterhold, Benedikt Günther, who are really in daily charge of the machine. So if there are any more detailed questions, I'm sure they'll be able to answer some of those. But let me start with a motivation, at least as I have seen it when we got into this whole business. I think, X-rays have been around for a while, yeah, discovered in 1895. But I think what then happened is somewhere in the 60s, particularly a little later when the highly brilliant synchrotron sources came up, there has been a split in the research community and also in the applications. I mean, basically, people really decided whether they go with and to synchrotron sources to do all the experiments or whether they actually stay in the lab and do continuous experiments. I think before that time, there has always been a fruitful interconnection, but I think meanwhile, people do either that or that, and they are mainly active in the lab when they need continuous access to these sources. For example, if you think about drug developments and small and associated small animal studies and these kind of things. So I do think that compact light sources can bridge this gap and bring together this community or parts of these communities at least to some part. This was my main motivation in the beginning. And I would also like to go back and comment on what Rod has said before. I think the gap is smaller in the higher energy range because there the synchrotrons are not so far ahead compared to lab sources. So now the question is if you either want to mainly complement synchrotron sources or if you want to sort of bridge the gap and use the best of both worlds. Yeah, anyway, to bring synchrotrons closer to the lab, yes, we need to shrink a synchrotron. The other people talked about the main concepts or main idea is essentially that we replace the standard laser undulator by a standing laser wave field, which can now be more on the micron range, and that allows us to use MeV electrons. I'm not going to talk more about that. There are certain rules, but if you then use about a micron laser undulator, then you can lower your X-ray energy to somewhere between 25 and 45 MeV, gets you to a gamma factor of 50 and still hard X-rays. And that's pretty much what we want. And we can now debate on how hard we want it. I'm not going to go into details because other speakers have sort of laid out that more nicely. We got into this business 2015 when we got the first and only machine from Lünzchen. And we installed it 2014, 2013, actually Lincoln installed it. And with many enthusiastic people, we inaugurated that 2015 and are actually happily running it in Munich since a while. This is an overview of the machine as it looks. This is actually based on a Lego model that some of the students has put together. So basically you will have a photocathode gun on one end where the electrons are basically generated by a laser. This laser is synchronized later, of course, with a laser cavity. And then we have basically 3 acceleration sections. And depending on how far we want to go up with the electron energy, we can engage them more or less as we need it. So as I said, we can go up to 45 MeV. Then there's some kind of a transport line with some refocusing stuff. And there's a pretty tricky instrument here on top, which is the kicker, which then basically kicks in a new bunch into the storage ring and takes out the old one. It's quite important to mention here that we do this 30 times per second, and we actually keep or preserve the emittance of the LINAC that we had before. So it's not operating in equilibrium, the storage ring. Now, on the other side, there's basically laser. It's a bow tie cavity. There's a laser amplifier, which is then basically fed through some additional diagnostics and preparatory transport equipment into the laser cavity, and then it's amplified up to several hundred kilowatts of power in the laser cavity. And then in the interaction point, this laser beam basically collides with the electron beam, and this can be viewed at now in the inverse Compton picture where you have a collision with the photon gaining energy, or in the undulator picture where you have a standing laser wave. Both descriptions actually get you to the same description of the performance of the machine. And I think in terms of physics, this is all quite understood. What is not so understood is all the nitty-gritty details of keeping this machine in a thermal environment and all these infrastructural related items that have been touched upon before. Yeah, here is a few more real-world pictures of that machine. This is the accelerator section. Looking from behind, this is the transport line where the electrons come from the LINAC. This is a view a little bit further from the back on the kicker, which is this shielded thing here on top. We also produce neutrons. This is why we actually have a bit of plastics around that too. That's a view on the laser oscillator side. Yeah, and that's actually the pure machine itself, but you also need, in order to be able to make use of these X-rays, quite a bit of X-ray infrastructure, and sometimes that's forgotten in these discussions. But if you come from the synchrotron world, this is actually quite extensive effort. So you need to build hutches, you need to build instruments, you need to be able to interlock these instruments and run these instruments together with the source, and this all together has to be somehow controlled by some kind of a safety interlock, whatever system. And don't forget that this is actually at least also 30% or 40% of this whole operation. So there also needs to be money to take care of the instruments all the way down at the very end of the X-ray beam line. So presently we have 2 hutches, one where we use beam sizes about 10, 14, 15 millimeters round in the first hutch, and one further downstream where we can let the beam travel and then expand to its natural width of about 65 millimeters, pretty much in a round shape. Yeah. Yes, and when you have a facility, of course, you need to plan that you have enough space for these experiments. Here's some overview parameters. I'm not going into all the details. I'll share the presentation with you later, so you can look into some of the. It's all also published, by the way. Yeah, so electron energy going up to 45 MeV in our case, laser power 350 kilowatts maximum, and altogether this brings us to an X-ray energy somewhere between freely tunable between 15 and 35 keV X-ray energy, and these are flux rates. So we are in the lower digit 10 to the 10 photons per second range, which is outperforming conventional lab sources and more at higher energies than at lower energies. But it's not really like orders of magnitude more, but it's somewhere nicely in between. Yeah, these are some values for the natural bandwidth. We have a 3% bandwidth, and this is sort of translated brilliance values, which is the unit that most synchrotron people like to use to compare to. Yeah, I'm going to talk a little more about what we have done and what we are doing with this machine. So this is how actually the beam looks like. We get out, now this is viewed at 16 meters from the source spout, and we get out a round and pretty homogeneous beam profile. It's quite boringly homogeneous, but this is also really nice. If you think about synchrotron sources, if you come from synchrotron sources, you never have such a beam. Yeah, all the synchrotron guys are now trying to expand their beams because virtually it's not possible to get a flat 2D illumination, which is also monochromatic on top, or at least halfway monochromatic on top. So this is a unique feature, and together with the let's say, relatively narrow bandwidth, natural small bandwidth, we don't need any additional optics. This is now what you can use. And we've been using and exploiting that mainly for biomedical applications, biomedical imaging applications foremost, but we have also looked at many other applications that we could translate over from the big synchrotron sources. I have a large background in synchrotron research before doing small angle scattering, a bit of diffraction and other things. So this has been the main driver for that research. And the first thing you can do, you just heard about tomography. It's a standardized technique. It's used in many, many applications. And the big problem if you do it in the lab is that you always get beam hardening. Beam hardening because you're using a broad spectrum. And what that basically means is that if you don't do anything against it, like applying algorithms or putting in a monochromator, you always have cupping artifacts, streaking artifacts, which are not nice. And if you're particularly after doing quantitative work on densities, 3D distributions, a monochromatic source will always be better in terms of giving you more detailed information on distributions of various densities in a sample. And this is just some profiles highlighting this. This is polychromatic spectra with a typical cupping artifact at the center. If you take a simple cylinder of water, and this is the Munich compact light source, which gives you a quantitatively exact measurement of the attenuation coefficient, and it's flat over this container. Yeah. At synchrotron sources, coronary angiography has been looked at for a while because you can tune in with your monochromatic spectrum right after an attenuation edge of a contrast agent. In this case, we had a little mock-up experiment with a pig heart and injecting some iodine contrast agent in the coronaries. And you see that you can nicely actually visualize them by tuning into the sweet spot after the attenuation edge. And yes, you can show that you get at least a 25% increase in CNR if you use a perfect spectral matching to the source. You can actually elaborate on that a bit further and do KH subtraction imaging, in this case by adding an additional filter, which actually has the KH exactly where the sample has it, and then you end up with two spectra, which you can actually subtract 2 times. And then you can also filter out other overlaying components. So this is also mock-up experiments where you have some rips, strongly absorbing bone in front of this heart with the contrast agents. This you can get completely rid of by this KH subtraction imaging and still then see the artery. So these are some kind of investigations that basically explore potential medical applications in future, because it has been done at synchrotron sources before. Yeah, we can do very nice imaging and also do phase contrast imaging applications of various sorts because we have a rather small source, actually a rather small source in both directions. And together with this homogeneous beam, we can nicely see, for example, propagation fringes. In contact regime, you only get the attenuation, and then as you propagate further and further, these fringes expand. and give you additional contrasting features. We have employed that a lot for doing small animal research, in particular preclinical lung imaging. This is very close in the nasal airways, where you see nice contrast in enhancement due to the edge enhancement. And this is now the full animal in the lung, and you see, of course, that you can nicely see more lung structure compared to a simple blurry attenuation image. And we've been doing that because we have a large focus on lung imaging here in Munich, and quite a couple of research groups interested in that. And that particular experiment was also done in collaboration, for example, with a group in Monash University that is also quite keen on this subject. You can do this dynamically, which is also extremely interesting, because this now suddenly allows you to study, for example, drug distribution, for example, aerosol-based lung drug distribution in lungs in mice, which is extremely important if you do drug development and also drug injection. And that is something is also quite unique, because we get this at one shot. At a large synchrotron source, you always have to scan. Remember, this very asymmetric beam profile. And this might also tie into some of the research that's probably important in Africa, if you think about coronavirus, drugs, stuff like that. And actually, one of our systems, another system, is actually used for coronavirus studies now. So this is highly influenced by how you actually prepare the aerosol and stuff like that. Yeah, besides propagation-based imaging, we're also quite active in grading-based phase contrast imaging, slightly different approach of phase contrast imaging that we have been using to characterize, again, lung diseases. We've been studying COPD in mouse models, also in a dynamic state, so you can actually look at how a mouse breathes and then look at the dark field signal, how this changes as a function of time. That gives you some insights again into distribution and also into potential models for how to deal with asthma in small animals and these kind of things. That is, by the way, also a very nice technology that has found its way out of the compact light source research labs, actually to a prototype in a clinical system, being used on patients, but actually then using, of course, conventional source technology. But started out at synchrotrons, we've been refined that at the compact light source, and now it's actually in daily use with patients. Another thing we've also been looking at, which is quite interesting, is bone ultrastructure. It's also a topic that is always done also at synchrotron sources to some extent. Interesting is that we can study the ultrastructural alignment of bones. And if you, for example, it's a conventional bone image, so attenuation, this is what we call anisotropy image. And you see that there's a region that appears much darker than this part of the bone. And this is now actually depicting the anisotropy. Here, the trabeculae are aligned predominantly in that direction. Here, they are not aligned, and here they are aligned again. So this is also something that might be very interesting in the context of bone remodeling and bone growth. And yeah, we're doing lots of work in that direction too. Outside of imaging, we've heard also that spectroscopy is something that is also requested by many communities. We've also explored that recently by coming up with a halfway clever alignment of silicon crystals and exploiting the natural 4 milliradian divergence of the beam. You can actually do energy dispersive X-ray absorption spectroscopy quite nicely. In our case, of course, in an energy range between 15 and 35 kV, because this is what we have right now. One thing that lies in there is, for example, the silver K edge. And here are some demonstration experiments that actually show that the MUCLs, so the Munich compact light source X-ray absorption near edge spectroscopy measurements that we, for example, did on different oxidation states and different solutions, powder and foil, that actually give you these very distinct and different wiggles for these different spectra, they actually look very comparable to what you get at synchrotron sources. And that actually really opens up a whole new community to address. And we do think that in particular higher energies, so when you are actually tapping into the K edges of gold at 80 kV or stuff up there, that becomes actually extremely interesting. By the way, it might also be interesting for battery research. Is something we are looking into, and a few other applications as well. Yeah, all this is backed up by quite a couple of press releases. We have a very active press department here at TUM. So if you want to read more about that, you can look at this or Google around. We've meanwhile published about 50 publications on the compact light source. Here's some 5 selected highlights. You can go to our website or write us if you wanna know more about the scientific output. And then, of course, yes, there's lots of people involved. I mentioned the team that is mainly responsible for running the machine daily operation Munich, Klaus Achtold, Martin Dierhoff, Benedikt Günther, and Bernhard Gleich, who is taking care of the facility. But then there's also lots of students, postdocs who have been working on specific projects over the course of the last years. At TUM, we are also presently heavily collaborating a lot with our laser physics chair, which is Professor Reinhard Kienberger. We are looking at upgrading the machine with a green cavity, which would then boost our energy to 70 kV. Very interesting. Of course, there's lots of medical collaborators, including my wife. She's actually a radiology here in Munich, and that gives us a first-hand insight. There's lots of people doing small animal research. I mentioned collaboration, for example, in Australia. All the folks at Linzien, also in particular, big thanks to Rod, who is joining here today. He has always been here and helping us and is still helping us. And finally, I would like to mention also now research instruments, which is actually slowly coming in because they will be helping us with running the accelerator part and maintaining that in future also. And there's, of course, a bit of funding involved. And with that, actually, I thank you all for listening. And of course, I'm here for any questions and discussions that this presentation might have triggered. Thank you very much.
Thank you. It was a very interesting presentation. Are there any immediate questions for Franz? So we have one more speaker, then we have a general discussion. So, Heinz Eberhard, if you're here, I see you there. Yep. So you can go ahead and share your screen.
Can you see my presentation? No.
No.
I don't see it yet. Nope. I think so. Franz.
Yes.
Are you still sharing?
No, I'm
Okay.
not the guild. I'm not.
Oh, here we are. Okay, there we go. Thank you. Perfect.
Is it okay?
Yes.
Okay. Thank you very much for having me on board as well. Since there are so many experts, I can easily rush through the basics I had incorporated into my presentation. Also, thanks to Fabio, who mentioned a little bit of X-ray fluorescence, but I have to make a few points. First of all, the motivation. I want to introduce not an alternative to the big machines, but a complement, kind of a low-budget X-ray technique for training, for later experiments at synchrotron, for later users on synchrotron beamlines. An installation of a large-scale facility costs a lot of time, costs a lot of efforts, and costs a lot of money. And learning by doing is essential to to get people involved as guests at such facilities and to get them trained. Those people at the moment would go to out of the country, would go to other laboratories, and maybe they never return. So it's better to get them trained at home, so to speak, with affordable equipment. And that is my basic comment I want to bring into the discussion. We know when we want to install a synchrotron, it needs several hundred million euros or dollars. When you install a compact light source, a few 10 million euros might be needed. For a portable X-ray fluorescence apparatus, handheld, you only need a few 10,000 euro. So many more people can use it on spot, more or less, in the meantime, until the big installation is running. So rushing through the basics, of course, nuclear physics and atomic physics, gamma rays and X-rays, no. And you also know the energy line in terms of a logarithmic plot. When you have the visible light in the middle and going to the right, you get the ultraviolet and then the X-rays and the gamma rays, or to the left, the infrared and microwaves, etc. You know that. In terms of characteristic of X-rays, we heard about X-ray tubes, the synchrotrons and the compact light source or similar. We have seen already the hand of the wife of Wilhelm Conrad Röntgen. In the early days, you had systems where you checked your child's foot, whether it fits the wanted shoe. So nowadays, that's not more done. The spectrum from the X-ray source is superimposed from the Bremsstrahlung spectrum and the characteristic X-rays from the anode. The synchrotron, you all know. We have seen from Franz Pfeiffer the spectrum from the Munich compact light source, the inverse Compton source there. But there are two features which should be kept in mind, especially for the younger people, for the younger researchers, graduate students, or whatever. For example, that is, what is transmission? When you compare it with standard light, visible light, we all know that light can go easily through water, through quartz, through glass. But if we apply, for example, a 1 millimeter glass plate to an X-ray beam, it's completely absorbed. And that is illustrated here with the mercury fluorescence line of the L lines coming out here, but with the glass plate, it's totally absorbed. So if you want to do it in a museum, in a glass-covered box or showcase, then of course you cannot do anything. You have to take off the glass lid. And the other feature is that the index of refraction for light, it is larger than 1. That's why we have lenses. That's why we can correct our vision easily. But in the case of X-rays, it is slightly below 1 always. And that means we need more sophisticated means to get a focused and a transported X-ray beam. That's why a beamline is so expensive, and that's why a beamline is so long. You need bright reflection, you need monochromatization for that, you need total reflection for the transport system, etc., etc. The interaction was already covered also by Fabio. So it all goes back to the atomic model, of course, where the binding energies of the levels increase with the elemental number to the squared. And that gives us a nice feature that here is a plot of the square root of the energy, or the square root of the frequency over the elemental number, where you just get the straight lines for the K lines or the L lines or the M lines. And that means by measuring the energy, you get a fingerprint of the atom. And when you have here the atomic table, the periodic system of the elements, you can nicely then identify just from the energy of the characteristic X-rays, the element. And the process is nicely, of course, explained by the photo effect done by Albert Einstein. When you kick out the electron, the energy stream, you then replace the vacancy by filling in from another electron, from the lower bound electrons, and you get either the fluorescence X-ray emission, or as an alternative, you get the Auger electron emission. And that one has to take into account that you have the competition between radiation coming out, the X-rays coming out, or an electron coming out. And due to the scaling of the energies, we have the full range from 13 electron volt up to 90,000 electron volts in the case of uranium. That is summarized here. You get the edges in the absorption cross-section. The cross-section actually goes to the power of 4 for the elemental number. And here is the here are the different lines coming out, the K lines. If you come down here, then one would have the L lines, etc. But the fluorescence yield, that is the competition between X-ray emission and electron emission. In the low Z regime, the elements around lower than sodium or beryllium, etc., and carbon and oxygen, there come out very little radiation, only electrons. On the high Z edge, there we get the X-rays and not the electrons. And that one has to keep in mind. In the case of the characteristic X-rays coming out, we have the so-called K family, K alpha and K beta. The typical structure is that you have a high intensity at the lower energy, a little bit 10% higher is the K beta radiation, a little bit less in intensity, roughly a factor of 5. In the case of the L family, one gets a more complicated structure, more or less a doublet, about half in the intensities, but some satellites. In the case of the M family, here in the case of uranium, we come back to kind of a doublet structure with satellites, of course, and the doublet is illustrated here. Now back to the mercury spectrum I showed already. That is the L family. That is the typical structure for the L fluorescence X-ray emission. With the nice feature of the edges, we can actually use the edges to filter out, in the case of X-ray tubes, we can filter out certain intensities in the spectrum. And that is done because of the feature that we have the absorption edges once you are over the binding energy of the next electron. Okay, in summary, it's an easy detection of an element. It's better, it's easier for if the Z is large, it starts at around 10 and goes all the way up. The quantification is a little bit difficult. If you have a complex elemental composition, then you get superposition of K lines and L lines and M lines from the various elements. So the analysis might be a little bit tough in complex systems. Therefore, you are much easier off if you have only high Z elements, because then the separation in energy is easy. But you have to be aware you only detect elements just by the signature from the energy, no chemical compound. If you want to determine what kind of chemical compound you have to go to different techniques. Radiation safety in terms of for handheld X-ray fluorescence systems is not so much of a problem because you can only go very close to the object you want to analyze, and typically about 1 centimeter. And if it is just at a wall or a rock, for example, then there is no problem. An open system, in open arrangements of the setup, you have to be at least about 1 meter apart from the system, then you are on the safe side. The total power consumption is in the order of a few watts in the X-ray beam, and that means typically about 100 watt or maybe up to 500 watts is needed to power the system, which is then for field studies possible with battery stacks, with power packs to be operational in field research. In the system here, shown here, it is the so-called AfLS system, which was originally produced by an Italian company. Now it's taken over by Bruker. That has the nice feature that the X-ray beam is focused down to 1 millimeter spot size. All the other available handheld, easily operational X-ray fluorescence pistols, so to speak, they typically have something like 6 or 8 or 10 millimeter beam spot. Field of application in metallurgy, metals, alloys, jewelry, in geophysics or geochemistry, minerals, soil, in archaeology, field research, cultural heritage, archives, museums, fossils, and of course others. You can go to medical application as well, wherever you have higher elemental compositions in drugs or in tissue, you can easily identify that. To give you some examples, an illustration of 20 years ago, we had the Deutsche Mark, German Mark, and the penny in that system, the copper penny, was almost entirely copper, only a little bit of iron added to it. So these are the typical copper X-ray lines, the K lines coming out. Nowadays we have the euro. We lost a little bit of copper, just a little bit. It's only 98.6% now, roughly, with a little bit more iron content in there, as one can see here. But it's still more or less the similar amount of copper. Here I have used my wedding ring. Nominally, it is of gold 750. And if we look at the spectrum, we have here the gold L lines, we have the copper K lines here, and we have the silver K lines around here. And we have about, instead of not exactly 750, we have a little bit less content of gold, something equally shared between the rest is between copper and silver. Ruby gemstones in bracelets, for example. Ruby typically is aluminum oxide. Aluminum has a Z of 13, which is at the edge of easily detectability. And that you can see in this spectrum here. The aluminum K line is here. Although the basic component in ruby is the aluminum oxide, more or less 100% aluminum, we only see very little K X-rays coming out. And that is because of the fluorescence yield, the competition between X-rays, radiation coming out, or electron emission. So that's why we have such a low intensity in the aluminum K X-ray. And we get a lot of intensity, at least it looks like, in the case for the concentration of the impurities or the admixtures in the system, like here the calcium, manganese. The value of the ruby pretty much depends on the impurities. And to give you a comparison, here you don't see any gallium. Many years ago, by a different technique, people were at the Louvre, were looking at rubies using as inserts for the eye and for the belly button for such an alabaster figurine. And they figured out here it was not done by the photo effect using an X-ray photon coming in, but a proton coming in, kicking out the electron. And they found, my colleagues at the Louvre laboratory, the CDRMF, they found a nice contribution of gallium impurities in these gemstones here. And that could be identified to rubies originating from the region in Sri Lanka or Myanmar. So the impurity tells you about the provenance of the gemstone or the minerals found. Okay, another example, rock paintings. And since we are dealing with talking about an African light source, I picked an example where I'm also related to somehow, because my son lives in Namibia. So that is an example of the Irongo region, rock paintings in the Irongo caves, etc., in Namibia. And that was done by a French group from Paris, with actually a similar system, an AfLS system mounted here on a tripod. And here a closer look, you see how close you have to come to the rock, to the painting, in the order of a few millimeters, so you are safe in terms of radiation safety. And so such an analysis was done in order to look for the rock paintings there. Another application is soil drilling, taking samples down to a few meters, etc., and follow the development of the soil. You get out a core, you split the core, and here in this case, such a portable system was actually mounted, and the core, the split core, was slided through the little housing here, and then the spectra were followed, and the spectra and the analysis was done of the elemental composition changing with the depth of the soil. So that is a geochemical application or geophysical application, actually, of a group from my university, Universität in Berlin. Now coming to my own project, here, the AfLS system, we use that in order to sort out papyrus, which might be used for tomography to identify possibly hidden text, to come to a virtual reading of text inside wrapped or rolled or folded papyri without doing it physically, without damaging, endangering the precious object. And for that, we needed the small spot of this kind of a portable system, the 1 millimeter, and one could actually do some mapping about 10 centimeter by 10 centimeter to identify high Z elements. And here that is illustrated with a mock-up you have seen already. That is the cinnabar, the mercury sulfide. There you get the L composition here. If one goes to the papyrus with no writing, there is actually nothing. That is just from the papyrus. And here was a symbol written with minium, which is the mixed oxide of lead. And that one can see here. The point is that the cross-section, as I mentioned in the beginning for the basics, the cross-section depends heavily on the Z to the power of 4. And here's a comparison between carbon, typically the constituent of an organic material, or carbon ink, for example, as well, or iron or lead. If we go to 30 kilo electron volt, then we get a drastic change from Z equals 6 for the carbon up to Z equals 82. And that is used here in the case to find out what about such a ink here from Arabic writing on a papyrus. In the papyrus itself, obviously, we get a lot of iron. The dust in the desert contains iron everywhere. It's from ochre, it's from rust, iron oxide, it is hematite, what have you. You have iron everywhere. So the signature for an ink is something different than iron. Here, in this case, we actually found copper. And that means one might have a chance if one would find such a writing, such a signature in a non-visible writing that could be identified by absorption tomography. Just the final example, and then I guess I am in time. That was a sample which was found in our archive, and you see in this region here, you don't see any writing. You see the black writing here from carbon ink, but nothing here. It turned out that if one does some mapping with our ELIO, setting a window on the LED L lines, that one could easily see a symbol in this area here. One can see it much better, of course, much clearer, with a better equipment on a beamline of a synchrotron beamline, where you have the sharp focus and where you have the, here, in fact, we did the K-edge sensitivity, going above the edge and going below the edge, subtracting it, then we could see and identify the lead ink written symbol over here. And that ends my contribution. I have to acknowledge, of course, a lot of institutions, a lot of groups, Egyptian Museum and Papyrus Collection in Berlin, the Hermann Center, where I was doing in my active time a lot of research, the SUSE Institute for the IT component, the Louvre, the Radgen Research Laboratory, and the CDRMF, which is the laboratory next to the Louvre, door to door. Thank you very much for your attention.
Thank you for a very interesting talk. So are there any immediate questions for the speaker? Then what we'll do, there's no questions, is just go immediately into, I think we are at the discussion part, right?
Yes.
Okay. Diama, do you want to start the discussion, or Simon?
Yeah, I will moderate. And I want before to go to the discussion, I think it is what I propose is to give like 5 minutes to people who want to ask, because we said that we will wait the discussion to for people who want to ask some questions to the panelists, because we decided that the presenters will are the panelists. So if you have people has some question, they could ask it before giving every panelist something like 5 minutes to answer to one question for the panel, which is what is the discussion, which is how, for example, the African regional infrastructure can do, and what is the matters toward developing a narrative about the role and description of the African regional infrastructure as milestones of the roadmap toward African light source. What is meaning? It is meaning how we can use the different type of CLS that people present here, and what they can be, how they can be used without being a compromising project concerning our light source. Because the problem is, we don't want, today our objective is how to install an African light source with fourth generation of five generation. This is the objective. But you know that presently we are lacking of, for example, equipment in African regions, human resources also, like the management, but also technicians, engineers. So what would be the milestones? What would be the role of a CLS to help the African light source steps roadmap to be at the end what you want? So but before giving people the to speak, I have only to make a little resume of what the presenters did before. For example, we have the first presentation is from Loen, and from his presentation we can see that the most important thing is how to find a win-to-win partnership. That is the important source. And he present also the ICS sources, which are good, but there is a lot know-how in making the source. What he said also some advantages of these ICS. For Luca, what I wrote is the principle of election scattering and the characteristic of the beam emittance depending on beam phases. And also he present that the storage ring base of ICS can attain larger fluxes, but need laser guru for, and it can only host one beam line, while for Linux it can host several beam lines. That is the difference between the two type of sources. So I think the other for the Linux-based ICS can generate X-rays beam from smaller spots, and other advantage is for example the example of star. For Fabio, what I can say is he present the lab scale of X-ray facilities, and in his presentation he gave some scientific background of X-ray scattering and different techniques and the possible characteristic extracted from powder X-ray and the application of powder X-ray and how detectors, how these facilities can be used in a large scale. For Pfeiffer, he presented the basic principle of inverse content source, and he gave the history of Munich compact light source and the X-ray extraction system. And in his, he gave also some example of application in clinical imaging. And for the last one is Meinke, he presented the motivation of such equipment, and also he gave the cost of the different type of light sources like synchrotron, CLS, and the low one, which is PXRF. And in his presentation, he gave us some example like the application in jewelry, etc. Finally, I have just one question for all of you. For example, what would be the cost? What is the cost, real cost of such CLS for everyone? The second question is, in Africa, we have some, we are not in the same level of access in energy. So what is the needed energy? I talk about the supply energy in the power. What is needed for any CLS? This would, but because our objective is also in the CLS and the African regional infrastructure and the AfLS to use a sustainable energy, this would be a difference maybe from the other light sources. So what is, can you give us, for example, the needed energy for such infrastructure? This is my question for all of you before letting you now to do few questions. Well, we have, for example, one question from, I think, Simon. And where does the community of people interested in developing CLS technology for focal infrastructure go from here? Do we need or want to start developing schools and workshops on the 1, electron beam physics, 2, laser technology, 3, mechanical electronical system, and 4, applications? The second question is, how do we bootstrap the commercial interest in accommodating research and development and manufacturing of CLS machines? How do we convince government funding agencies that this is worldwide technology? This is the second question. And the third one, how many orders would it take to make it worldwide, to invest, to investors, be they some private corporation, some venture capitalists, or some government? Well, that is the questions from the Zoom. So I will start for maybe for the first presenter. Maybe, yes, Lewin, Rod Lewin, if you are here.
He's departed already.
Ah. So we can continue with the second one. Lawrence, maybe Lawrence has something to do.
So I actually put a few questions in the chat, which people can either pick up and answer or totally ignore.
I can ask, what is the research agenda for improving the technology? That is your question for the panelists.
I would turn that around. I don't think any of this is commercially viable as a business. That's why Rod said it needs a research partnership. I think that's how STAR was produced. I don't think Africa can promise to make any real attempt to keep it alive commercially. So I think the way forward would be first to secure funding for a research partnership, just for one. I don't think we can jump into N. So I think we'll start somewhere with a research partnership, which is all the different people who could contribute, and we develop the proposal together. So I think Rod is quite right. We shouldn't be looking at it, as if we're going to make a profit and someone can run a business. But there are people who would be very interested to look at it as a research partnership. And then within that research partnership, I think the training will come. So until we get the project going, young people won't want to just attend a workshop when there's nothing really there. So I would say step one is for us to write the motivations and the proposals and lobby them and achieve that research partnership. I think we need, therefore, a narrative, and that's what today was about. And I think we see a spectrum of facilities. For example, from Eberhard, his last application, it's exactly the narrative that we want. It's a highly competent research tool, research instrument, highly competent. It's not expensive. And he managed mapping. I'm not quite sure how he managed it, but maybe there was a translation stage that moved the sample around, and he managed mapping and found hidden character. And that was powerful motivation to go to Bessie. I don't think Bessie would have believed in that sample as having a hidden character if he didn't first manage mapping. So I think what his last research example showed is even the very, very entry-level facility, which should be affordable for many African countries, it found something very interesting, and that could lead to research at the synchrotron. And that, for me, is the story of the local research infrastructure or regional research infrastructure. It's highly competent in its own right, but it also is part of building skill and producing output that eventually improves the logic of a synchrotron. And then I think all of these that we've heard today, from the handheld, from the lab scale, and the CLS, they all complementary. And I think if we have that narrative, they don't, not one of them replace the advanced light source, what we want to achieve with that, but they all part of the roadmap with milestones that build the community, build its capacity in humans, capacity in infrastructure, capacity in technology transfer. And they build that, and then with that logic, as it's a comprehensive proposal, we can form the research partnerships that Rod spoke about, and it will attract the friends that we have from overseas to partner with us, and then together I think we can go forward. That's how I would see it.
I could answer the question concerning the mapping.
Yeah, Manke, yeah, you can. I see your hand.
Yeah. The mapping was, you have seen the picture, the photograph of the system that was with two motors going into two different directions, not in the Z component, but only in the X and Y component by 10 centimeter in each direction. And that's why we have chosen the 1 millimeter diameter system that one can easily scan half a millimeter steps, etc., to have it not so extremely long, time consuming.
Okay. Okay.
Can I make a comment?
Yeah, you can look.
Yeah, I like to really share and underline the point on training and education that was mentioned by Simon. I think is, as a first step, one of the most critical initiative that you have to undertake. Prepare people, build the expertise, clearly starting at the beginning from qualified collaboration with institutions, person who are already expert in the field. But building up the expertise is the very first step. And if the African Light Source Initiative is based also and distributed over university campus in Africa, the training and education should come for free because it should be in the mission of any university collaborating with this big initiative. Because in any case, if your dream is the 4th generation light source, you need to develop a dedicated team with all the know-how that you need from machine. I showed something in my talk, but of course you have so many aspects and different fields of expertise that you have to be able to develop with young people, students, training, education. Clearly, organizing workshops and schools is a must. And as far as I know, in the context of the African School of Physics, some of this activity has been already being done and is in progress. So my point of view is really this is a very important and crucial step that you should undertake.
Many thanks, Luca. And I don't know if Fabio, you have something? Hello, Fabio. I think Fabio is out. Yeah, Simon, you can.
I think there's first an important comment from Trevor you should deal with.
Do you want me to say it, Simon?
Yes.
Yeah, I think you can develop your comment a little bit.
Okay, can you see me? Okay. We have quite a nice rotating anode machine in Cape Town. And the problem has been that maintaining it is beyond the budget of the university and indeed the region. There is no real organization, and we didn't actually think this through adequately. We designed the whole system in a time when there was a lot of money around coming largely from foreign sources. And indeed, foreign sources paid for most of the equipment. So without foreign influx of money, it's actually extremely difficult to keep systems running. And so we can't, if we don't have a system to run, we can't actually build a community around that system. So these are real problems that I don't know how we can solve in Africa. And I think that they're going to get much worse if we try for more complex apparatus.
Okay. Okay. I have a question from Simon also.
Can we just chat a bit on Trevor's point? So it's exactly that problem that we're not having our governments take responsibility for this. So I think that's part of our work to do, that there must be that funding not just to purchase the system, but to maintain it, develop it, and operate it. I think that's very, very important. I think it's the work of our community. I know that Trevor built a huge capacity in his career, and there hasn't been the follow through in order to maintain it. But I think what Trevor's saying is there's a valuable role for the lab scale facilities, but there's a very, very important caution that the operational budget must be part of it. And I think that's the warning that we've got to take going forward. And I think it's so important that African governments understand that.
Okay, thank you, Simon.
And Trevor's at an additional point, and I'll just mention it because he mentioned also the sample prep. So it's not just the X-ray machine. It's all the preparation, all the ancillary infrastructure that must also be in the budget.
I would actually like
Yeah,
to
5-4, yeah, go on.
I'd like to comment on Trevor's comment.
Yeah, go on.
I fully agree that running the machine is quite a challenge, and yeah, it takes about 10% per year of what you roughly invested initially to do a good job, and you need to budget that in. However, I do think that such a African light source, compact light source based instrument, this is not a standalone large-scale instrument like a high-end electron microscope that you are buying and running on yourself. It gives you, and this is also what Luca said before, it gives you a stepping stone in terms of education and also in terms of tapping into the larger synchrotron community within Europe or worldwide. And this collaboration, I mean, the synchrotron folks are quite friendly and they are always willing to help. I mean, if you approach these in Hamburg or the ESRF in Grenoble or other sites, I mean, if there's an activity somewhere, I mean, they have also been sending older parts of machines to Israel, isn't that true? Or where is it? Jordan? I don't know where the last one went. So it's not a machine that you buy and then you have to deal with it yourself. You are basically using this as a stepping stone to tap into a larger community, which will happily help you and support you with whatever they can do in collaborative grants and networks. And speaking for ourselves in Munich, I would be more than happy to strike up or come up with a strategic partnership. I think our university actually has some kind of partnership with Africa or some institutes. So if we can help in any way, we will certainly do. There's also DFG Africa collaboration programs where one can then tap into. So it's also a chance that you are having here, not only a challenge. This is what I wanted to say.
And let me just comment briefly. We have had the START program, which was funded by the STFC. The amount of money that they put in was about 80 million rand. And this involved training people at Diamond, both in X-ray crystallography and in all techniques, synchrotron techniques, and indeed in electron microscopy. So the program was extremely valuable, and the support that we got from the British was immense. We are currently busy writing an MOU. Well, the very first MOU we had was with EMBL in Grenoble, where we had an extremely fruitful collaboration, which actually got us working in the whole synchrotron field. And it was wonderful. That was with CUSAC. And eventually, and now we're negotiating a collaboration agreement with Goethe University in Frankfurt, where it's envisaged that we will collaborate in a wide range of different techniques, ranging from electron microscopy to X-ray diffraction to mass spectroscopy, and so on, so that we will be able to develop our whole ecosystem for bioscience structural research. But on the other hand, it's not happening here. So all of the equipment, and oh yes, the other thing is that we've also signed up as a partner in Instruct, Eric, so that we have access to the equipment in 27 odd labs, so for the structural biology. So that's also been very fruitful, and many of our young people have been on training missions to those centers, so that we've tried very hard to utilize the European infrastructure to develop our young people and to develop our science. But I was just commenting on the difficulty of running equipment in Africa, which is greater than anybody can imagine.
Yeah, thank you. I just want to ask a question for everybody. It is about the human resources training, and this I want to know if you have some example of collaboration that your compact light sources or infrastructure facilities had to facilitate the training of people coming from, for example, other, and what is the kind of how to use a collaboration facilities or funding, how to work in partnership to find funding for facilitate this kind of training for African PE researchers, because this will be one of the difficulties of such infrastructure. Yeah. It is a question.
I'm not sure if I understood your question correctly, but is it about funding mechanisms that would allow us to do collaborative projects with you guys going in that direction?
Yeah, no, my question is if you know, for example, if you know an example of collaborating in training people coming from, for example, other countries, our regions in the world, to your CLS, to your facilities by collaborating partnership to make a training, something like this. For example, if you host students, researchers coming from other countries, this example, if you have, and how you did it, how they get funding, it is collaboration with your CLS or it is a collaboration with our other partners. This is my question.
I mean, I can quickly answer for how we deal with that in Munich. Basically, our machine has been applied for by a joint consortium here in Munich by both universities. So this is mainly 4 PIs or 4 larger groups on laser physics, X-ray physics, and on the clinical side. Yeah. And besides that, we don't have much additional bureaucracy. So when we want to collaborate scientifically, we can basically invite or have anybody joining with whom we want to collaborate. It's really based on a personal basis. So I mentioned Australia before. This is a person, Kay Morgan. She has been working with us as a postdoc and repeatedly expressed interest. So we had many PIs or people coming from there. more national. I mean, this is just collaboration partners who are scientifically interested and willing to collaborate. Our condition, of course, is that there's joint science produced publications. But apart from that, we don't have a fixed model that requires people to pay something or do something. And now when we are talking about hosting people, we have been doing this. Our university has particular collaborations with particular other host institutions, but actually that doesn't really matter. If we want to collaborate and if you want to send a person over on a graduate level or on a postdoctoral level, we will always find a way of making that possible. If we need financial support, we have various mechanisms on the regional, so the Bavarian, or on the German level. The German Science Foundation, DFG, has various exchange programs, also the Helmholtz Foundation. And I think if somebody is willing to come over for half a year or a year as a postdoc or whatever, I mean, we will easily find a way of supporting. It's probably more difficult on the undergraduate level, but there, I mean, you typically don't have people directly working in the machine. There you're talking about joining a study program. But that is also possible in Germany because we still don't have any study fees.
Okay.
So in that way, it's not formalized for us, and whatever works and makes sense, we can do.
Okay, thank you. It is clear. That is my question. It is really clear.
Oh, Diuma, if you like, I can try to at least partially answer your question.
Okay.
As far as STAR is concerned. Because STAR didn't start operation yet, there is no plan for the next year, at least until the end of 2024, to give beam time or access to the user facility to external users. Next year it will be a, let's say, commissioning period time for the source and the whole research infrastructure. I know that the host institution, University of Calabria, is planning to set up a consortium with other Italian research institutions, as for example my institution, ANFN, and also others, Synchrotron Trieste, CNR. And in the context of this consortium, they are looking ahead to handle the access and the beam time to external users. Concerning instead visiting guests, visiting students, University of Calabria is sort of very similar to what Professor Pfeiffer said a few minutes ago. So there are exchange programs for external students. Some of them are funded through European government funds. So for sure, because the laboratory, the research infrastructure is inside the university campus, and under this aspect is very similar to MUCLS, all the exchange of research personnel or even students is facilitated by being in a university campus. If you need more specific information, of course, I can put you more in contact with my colleagues from University of Calabria. Professor Agostino was in the meeting and he left, but of course, we can give you many more details. I can tell you that, for example, they are hosting students coming from Latin America universities in Ecuador, and as far as I remember, Bolivia. So they have a quite strong program of for visiting students.
Thank you, Luca. Yeah, this is my question because I know that we need in the roadmap of the AfLS, we need to train human resources. So it is important to know who can be our partners, our collaborators, who can host students for training. Yeah, outside the summer school, something like this. It is important to be in some CLS facilities to understand how it works, how it is managed, something like this. It is for that I asked this question. Yeah, so thank you for your answer, and maybe I think we come in the end of the discussion. If anyone doesn't have something to say, I think I will maybe Simon, you don't have something to say? Because before closing the discussion, I think he's outside.
Hi, can I say something? Sorry, I'll just barge in quickly. I can't put up my hand, sorry. So yes, I think it's been very encouraging to see that there are intermediate steps in the process of getting to a full synchrotron. You can go for a compact system, but of course, I think what is really becoming clear is that as part of that whole project, we would need to make sure that there is not only money to build the facility, but to really maintain the laboratory around it, to have travel allowances so that people can travel from other parts of Africa to the to the light source, wherever it is going to be. And I think that's just really the main point, that it's not a matter of just a once-off batch of money, but that governments need to commit probably for a period of 15 years from the outset, that the whole infrastructure can work. And I mean, as soon as there's basic agreement that this can go ahead, then I think it would be invaluable to send the appointed team, and at that point you would really need to start investing in people. To have them travel to various European or American, South American places to really get proper training so that they can run the facility from the day. But one of these compact light sources probably is not going to be, or doesn't need a staff of 100 people. You might be able to get away with a staff of 10, 20 people, but then you need to have at least as many again, who can do sensible experiments, and you need a bit of labs, etc. So I think that the budget is not out of the world, but it is, people need to budget for all of these things for a period of a number of years. And then once commercial users, etc. come in, then there might be a case afterwards to really get additional funders to get, well, I don't think that will ever carry itself, but I mean, at least that will indicate that there's interest beyond just academia, and then governments might be prepared to provide more money. But I think that will be the important parameter to make sure that the whole plan incorporates enough funding that all of these other aspects can be covered as well. But thank you, everybody. I think it was a very good overview that we had this afternoon. I learned a lot.
Thank you, Jetta, for your participation. And Simon, I think we will stop here, and we will come back to everybody, and we thank again everyone for your presentations. And if you accept, we can use also your presentations for our document that we have to present to the AfLS CDF document. So if you give us this possibility, we can use it. We can take some parts that is very important for us. And again, thank you, everyone. And maybe we will come back to you for more advices concerning the African regional infrastructure like CLSE. Thank you, everyone.
Thank you. Thank you.
Bye.
Thank you.
Bye-bye.